loves chemistry 'cause it's fun. That makes it crazy, then he's the one to teach you chemistry 'cause it's fun. He's chemistry coach. He's chemistry coach. All right. So we just finished watching, I hope you just finished watching some reaction videos. If you have not yet, go back and watch my reaction to the reaction videos #1, and then you will have seen at least, oh, hang on a second here. You will have seen me reacting to these, okay? So if you don't want to see me, you can at least go watch those videos right there, and you'll have a good starting point for what we're going to go off of from here. So our objectives here today are to look at temperature, surface area, catalyst, concentration, and pressure, and see how those things affect the reaction rate. And then we will look at enzymes, and we'll see how enzymes work as catalysts in living systems. So we want to be able to explain the reason that each of these different things, like temperature and surface area, etc., are able to affect the rate of the reaction. And then you want to be able to look at enzymes as proteins and see how they can affect metabolic processes and give examples of them. All right, so just remember that reactions don't have a single specific reaction rate. The reaction rate is actually going to change over time depending upon what happens, but as a reaction proceeds forward, then your rate is basically going to approach 0 most of the time, right? So it's going to slow down, typically going towards 0. So conditions around a reaction are going to affect the rates of that reaction. Remember that all of the rates must be determined experimentally. We will not cover in this particular lecture how to determine those actual rates with regard to the formulas, but the formulas that we actually come up with, they're based upon experiments where we actually take and divide the completion of those reactions by each other, basically. All right, so let's talk about the first one, nature of the reactants. So depending upon what material you have, that's going to affect the rate of your reaction, because some material is going to react more than others. For the example that you guys had just watched, you watched one that had the catalyst as its main emphasis. Well, the example on that one, they had one tube that had the manganese dioxide, another tube that had lead dioxide, another tube that had, lead 4 oxide, manganese, gotta try to remember 4 oxide, lead 4 oxide, and then iron 3 oxide. And you notice that in those 3 different tubes, there were 3 different reaction rates. Okay, so just to kind of refresh your memory on that one again, it was this one that we were looking at, and on that particular one, you had the manganese, the lead, and then the iron, and you can see that with those different substances, let's take it back, with those different substances that you had different reaction rates, okay? And, oh, there we go. Take me back, where are you? Where are you? Where are you? Where are you? There you are. There's the manganese 4 oxide. Was that first one, and then right in between was a lead 4 oxide, and then you had the iron 3 oxide. So anyway, nature of reactants. You have different reactants. You're going to have different speeds of reactions. So the types of chemicals are going to affect the reaction rate. Iron rusting won't take place at the same speed that C4 detonating does. All right, next one is the surface area. In this particular, we're talking about solid reactants, and the demonstration video that you saw had the milk powder, or what I like to call non-dairy creamer here in America. I'm sure we could find dried milk. I know I've found it before. I've never tried to light it, but I'm sure we could try to find some and light it here as well. Anyway, so as you are increasing the amount of air that's exposed to those particles, then you're going to allow for the oxygen to come in, and then all of those tiny little particles can actually combust. If you remember in the first example, you didn't see it burning, even though the flame was right on that little pile. It charred the top of it, but it didn't flame up, right? And so the big thing to keep in mind there is that you have increased the surface area by having it all broken up. Allows for the oxygen to get in there and allows for that combustion reaction to take place. Now, this is obviously really dangerous. You can see the example here. We have a grain silo that apparently has had a very unfortunate accident. Oh, look, there's a little guy down there. I don't think I ever noticed that little guy. Where are you? You're like, I'm over here. Whoa, man. Inadvertent mouse clicks. Curse you, inadvertent mouse clicks. All right. Anyway, so yeah, in these grain silos, you can have these discharges of static electricity, which cause huge explosions. And so supposedly in these types of silos, when you go to work, you have little cables that will ground you so those sparks don't happen, and so you have to hook in as you're moving place to place so that you don't have static discharge that builds up. And of course they have to have really good ventilation systems. If the ventilation system starts going down, you get all that powder just kind of floating around in the air there, then that's a really dangerous scenario for an explosion to happen. This one you can see in the slide there occurred on June 8, 1998 near Wichita, Kansas. Killed 7 and injured 10 employees. So surface area affects the rate of the reaction. All right, next one, temperature. Now we saw the demonstration of the light stick, where you had one that was warmer, you had one that was cooler, you had one that was kind of in the middle, and how you had different rates of reaction because you had different light coming off of each of those. Remember, for temperature, you can have some pretty big impacts. For many reactions, a 10 degrees Celsius increase in temp will double the reaction rate. And again, what's the deal here? What's happening? You've got faster molecules, right? That's what increased temperature is, a higher average kinetic energy. These things are colliding into each other at a faster rate, and so you're going to end up having a faster rate because you have faster or more collisions in this case. And the more collisions you have, faster energy, activation energy, remember that from previous lesson, and then you're going to end up having a faster rate. Now, on this diagram, I think it's kind of important to take note really quickly. Some interesting things here. You can see that we've got these locations there and there on the blue graph and the orange graph, and you can see what's happening. The average kinetic energy at 35 degrees Celsius on this orange graph versus the average kinetic energy at 25 degrees Celsius on the blue graph. So this is basically showing you how many molecules at a particular energy. So if we look at the total amount of energy here for the blue one, it's a little bit cooler, right? So at 25 degrees Celsius, most of your molecules, this is the number of molecules over here, so the most of your molecules are averaging a cooler temperature than on this orange graph, where most of your molecules are averaging a warmer temperature. Now, what you will notice is as you see these types of graphs, and if you see these later on, that you will actually end up getting the higher temperature graphs end up having lower and lower and lower peaks. And so what that means is you end up getting a bigger distribution of molecules at the varying temperatures, instead of having a really high number at a particularly I don't know, middle temperature there. You end up kind of flattening that curve out a little bit. Flattening the curve makes me think of COVID-19. All right, so that's temperature. Kind of interesting to take a look at that. All right, and then our concentration of our reactants. And again, in the video with our British friend here, this was one where she actually asked a question at the end about about whether or not we should have maybe looked at the number of moles instead of the number of grams to make sure that we were having a fair test. And so there was also one previously where we saw another elephant toothpaste demonstration with Mr. Carlson, and he showed us that at 30% concentration, it was definitely reacting faster than at 3% concentration for that elephant toothpaste reaction. So more reactants means more collisions, and if you're dealing with a gaseous reactant, then if you increase the pressure, then you're going to be increasing the number of collisions as well. Okay, so you could decrease the volume, increase the pressure, and you're going to speed up the rate of reaction also. All right, and then finally, catalysts. Now we go to our good friend platinum. Inside cars, catalytic converters, you have sometimes platinum, sometimes palladium, sometimes mixtures. But the idea for a catalytic converter is to try to take some of those combustion products that did not completely go to completion of making carbon dioxide and water, and it tries to make sure that that reaction then continues to take place. So it reduces the amount of carbon monoxide and then some other chemicals that wouldn't have reacted even though we would have hoped they would have. So catalysts like platinum are basically trying to lower the activation energy. Okay, so that's the emphasis that we want to make here. They're trying to lower the activation energy, and I just did an inadvertent mouse click again, so this slide is going to go to the next page. But before it does, let's take a look at this little part here, not lifting my little pen. Remember that it doesn't change the enthalpy or the delta H, nor does it change the equilibrium position. We'll show you what that means on the next slide with a little graph. It's just changing the activation energy, and so it changes the speed of the reaction because it doesn't have to spend as long trying to get up to the top, okay? Oh, we get ready to go already. There we go. Wasn't such an inadvertent mouse click after all. We were okay. All right. So let's look at that equilibrium position. I wanted to talk about that. So the equilibrium position is going to be that place right up here where you end up with your activated complex. And so you can see that as the reaction is proceeding, your reactants are turning into products. If you can lower this activation energy, right, you're lowering that energy, then that means it doesn't have to take as long to get up and then over. So you're going to speed the rate of the reaction for each of those different chemicals that are reacting with each other. And it also, if we talk about equilibrium, actually really would probably be talking about the equilibrium here between whatever products we have and whatever leftover reactants, if there's a two-part reaction as well. This is really probably where you'd be talking about equilibrium more than up here, like I had just said. So, I mean, it's kind of like an equilibrium up at the top. You've got the reactants turning into the products. Let's just pretend like I didn't say it and go on. All right. And here's our enzyme. Let's just take a quick gander at what an enzyme is doing. The enzyme is a protein. Okay, so this is actually made up of a whole bunch of amino acids. Okay, and the substrate is going to be another substance that is probably made up of various different types of particles, could be another protein. But the substrate is going to fit into what's called the active site of the enzyme. And when that does that, then it has the ability to break up and it forms into the different products. that you have. So enzymes are trying to lower the activation energy. A lot of times these substrates just will not react until they get to an enzyme. The enzyme allows them to break up. But before that, those guys just kind of stay together. So unless heat or something would damage them. So enzymes inside your body are great. And one of the enzymes that you could again refer to the example that we had over here with Our Lady and the potato. The enzyme that is interacting with hydrogen peroxide is called catalase. I'll show you that on this next picture here. But you've got some enzymes that are in your liver that are interacting with catalase. Now, if you guys remember, the last one she showed you over here did not have a reaction taking place, really, right? And remember, that was the boiled liver. And the boiled liver is going to be the one that had its enzyme destroyed. So heat will come in here, and heat will just go, just destroy these little enzymes. And so that they can't do anything. So while this might have been catalase that would have been able to break up the hydrogen peroxide, it can't do that anymore because it's been denatured, it's been destroyed. Okay, so let's go on to this final graph where I can show you the decomposition of hydrogen peroxide. Now you'll notice that the energy is different for each of these. The uncatalyzed reaction is up here. It's going to take the most activation energy. And then iodide can create a lower peak. The manganese dioxide can create an even lower peak, and then the enzyme catalase can create the lowest peak out of these. So if you looked at this graph, you should be able to tell me which one would have the lowest activation energy, the catalase, right? And which one would probably have the fastest reaction rate. Probably going to be catalase, right? So that is what that graph is showing us. So we can now today. We've done it. Here we are, we've accomplished something amazing again. We can explain how temperature, surface area, catalyst, concentration, and pressure all affect the rate of the reaction. Not only that, but you can tell me why. Okay, so let's go to that again. How does temperature change reaction rate? More collisions, right? All right, that's going to make it faster. All right, so then surface area. More opportunity for collisions. Okay, increased surface area, more opportunity for collisions. That's going to speed it up. A catalyst. Catalyst is actually interacting with the chemicals and actually breaking them up. One thing that you want to remember about a catalyst is that a catalyst is not changed by the chemical reaction. So platinum is still platinum after it's done. It doesn't change into like platinum oxide or something, okay? It's just still platinum. Catalase, for instance, would still be catalase after it did the reaction and helped break down hydrogen peroxide. Concentration. Well, yeah, that kind of makes sense. So I get more molecules, more particles. I'm going to end up having a faster rate because I have more collisions. And pressure. Remember, pressure can increase the number of collisions as well. That's what pressure basically is, so that would increase the rate. So now you can tell me what each of those does. Okay, you can tell me how each of those is affecting the reaction rate and how that works. And you can talk to me about enzymes. You know that enzymes are proteins, good job. And then we've seen some good examples of where an enzyme is actually at work. One of the enzymes in your saliva that breaks down starch is called amylase. So there's another enzyme that you are very familiar with, even though you might not have known its name. Amylase is in your saliva and it helps you break down starch. All right, well, again, we have learned some chemistry, and it has been a great time. You've had some fun. Maybe not as fun as you had watching my reaction videos, but we had some fun. We learned some good chemistry, and you're seeing the beauty of chemistry in your world, and hopefully you're going to be able to use this in your everyday life. All right, have a good one. This is Chem Coach Powers, signing off.